it seems to me that people are still having challenges with 230 2 cosine omega t plus. I gave something like this, and I still have people doing this when I ask for the voltage phasor. 230 angle 0 degrees. Actually, the one where there was one V of t, I think is 169. That was the one, cosine omega t. Forget about this one for a second. I still see a lot of people were doing this. I is equal to 169 angle 0 degrees. And I was a little concerned because I thought maybe I wasn't clear that this is the peak value. And this should be the RMS value, which is divided by the square root of 2, which I think it gives 119.5 angle 0. Oh, that was voltage, I'm sorry. Something like this, right? So if you still don't understand this, like I said, just come by and let me know, and I'll explain that again. I mean, I won't do it in class because I think it's, we already have gone through that. But that is important to understand and be able to manipulate that. The other thing that I saw in some cases, I asked for phasors, and I see people doing this. V of t and I of t. And I think I said it a few times. This is a time domain. This is if you write this, you're talking about this. If you write that, you're talking about this, right? Talking about sinusoid. So you have to remember that this is I. It's a phasor, has a magnitude and directional angle, and then V, same thing. You have a magnitude and some sort of directional angle. Like I said, not a lot, but I see some people having a problem with that. The other one was on the power factor. When I was asking for the capacity, I think this was the one. Yeah. So when I say most people were able to find the new angle, which was cosine inverse of the new angle, whatever, new power factor that they give you, I think it was 0.8 something, say 0.85, right? I had quite a few people struggling with this, finding the angle. The other thing that I found was this, the Q cap. It was Q load. This doesn't change, and I keep on saying that doesn't change because the load is the load, right? And what the Q new or what the new bars that the system is going to supply, meaning the grid, right? I saw a few people, like some people get everything, and then when we got here, they got confused. They didn't know what to do with that. So again, if I mark it down and I put notes there, and you want to come talk to me, I'll explain this again. That was that. The other one where I had quite a few people. No, this was not this. Second one was fine. Yeah, that's the one that I told you where I had a few where they had this 169 angle 0 degrees, and then you had a resistor, you had an inductor, and you had a capacitor. This was negative, and then you have an RJX, this 3 loads. And that one was fairly simple. You get a square root of 2. You just divide the voltage by the resistance, the voltage by the reactance of the inductor, the voltage divided by the capacitance, and then the voltage divided by R plus JX. So it was, like I said, once you find this voltage, it was just finding the current and finding the current in the time domain. Some of you didn't put the phasors, but everything was fine. I gave you full credits for that, but just remember that I did ask for phasors, to plot the phasors. I did have a couple of people, not a big deal, but again, I asked for the phasors and they were giving me this, I of t and V of t. And they explained this should be in phase, this should be 90 degrees, but that's not the phasor diagram. This is time domain. And remember I said that, right? Usually we don't give this as an answer in this type of problem. We want the phasors of it. Let me see, what else did I notice on this one? Um, I think that was it on that one. Like I said, there were there were a couple of people who used numbers. Like I saw one that on the resistance, which is not really a big deal. Oh, on the current. That was on the current. On the resistance. Yeah, I saw just maybe one person that used 20 ohms instead of what I gave, which was I believe I gave, was it 10 ohms that I gave? Yeah, I give you full credit. I went to the answer. I thought, maybe they saw a 20 instead of a 10. So no big deal, as long as you can follow that. Um, and on the last one was really simple too. There were three loads. Basically, it looks like this. There was a load here, there was a load here, and there was a load right here. And if I'm not mistaken, one had a power triangle like this, the other one had a power triangle like this, and the other one was just straight because it was a purely resistive load. A lot of people miss this right here. This was minus J40. So when I have the Q total, I had quite a few people actually who did this. Whatever value was for Q1, and then instead of subtracting this, they were adding it 40, and they came up with a 72 something, which messed up the power factor. And that's the piece that I want to reemphasize. If you have a resistive capacitive load, the J is negative, it's not positive. It's positive when it's an inductor, it's negative when it's a reactor. Um, that was it. And like I said, for those of you who had the process right, I just wrote a note there and I told you please review the solution. In some cases, I actually wrote the formula. But as I said, for the most part, I think everybody did pretty okay. And you know, this test was really easy. It was meant to be super easy. Not that I'm trying to scare you, but the only thing with the final is that there's more topics on the final as far as, you know, problems that I will give you. This one was, I thought it was fairly straightforward. So, but I'm not saying the final is going to be a lot harder. I'm just saying that there's more things that you got to remember with formulas. Like I said, I'm guessing that some people didn't write formulas on the cheat sheet. So take advantage. I'm giving you that as as an opportunity so you don't have to remember something. I'll go through my notes. If there's something that you don't understand, come back to me and say, I really don't understand this. Like, what do you mean I have to divide by the square root of 2? And I'll explain it again. I have no problem. Okay, just want to make sure that you're comfortable with it. All right, let's go back to transformers. Like I said, I'll upload this solutions. I just got to find out if the people that are missing, they still need to take the test. Or maybe I just upload it, and if somebody has a missing test, I just give slightly different problem. So, okay, so we talked about this, I believe, right? Let me just do a little refresher. V1, E1 plus minus E2, V2 plus minus, and we talk about an ideal transformer. This is I1, and obviously this induces an current I2 through this winding. We talk about the N1, the N2. We said that A, which is the turns ratio, is equal to N1 over N2. I think I talked about this. And I mentioned that the thing about ideal transformers is that you're assuming that the power that goes in, P in, is the same as the power. Actually, let me do it this way. S1 and S2 are equal, meaning S1 goes in, S2 comes out, because there is no losses that you incur on an ideal transformer. The challenge with an ideal transformer is that the only thing that you can do if you're running some sort of model, that your voltages are all ideal, and we'll talk about that. Let's see. Yeah, so that's that. So let me work a couple of examples for ideal transformers before we get into non-ideal transformers. In MATLAB, as a matter of fact, I'm gonna see if I can build a couple of models for you on Simulink. You have the ability to do that. You have ideal and non-ideal transformer models that you can utilize. So example one, let's say one. We said that an ideal transformer with a secondary impedance connected to it of Z2 equals 1, sorry, 1 plus J 4 ohms. The transformer has a turns ratio with a turn ratio of N1 over N2, which is equal to 5 to 1. Let's see. And we're gonna say find. This is very simple. Find. Draw the equivalent circuit. As seen or referred when seen from the primary of the transformer, and then B for a source of 120 volts at primary of transformer find the current I1. Okay, so basically what we got is this. Here's our transformer. And as I said, it's an ideal transformer, so there's no losses on it. And when they say here, a impedance of Z2 is connected to it, that means that there's a load. That's what that means. That has nothing to do with the transformer. This right here is not part of the transformer. You can think of this as the load attached to it on the secondary side. So that's what they're telling us on the secondary side because it's Z2. The question also is asking, so then in that case, E plus minus 1, E plus minus 2, and this will be V2 plus minus, this will be V1 plus minus, and here's I1, and here's I2 for this transfer. Okay, so they're asking us again to draw the equivalent circuit as seen from the primary side, but the load is connected on the secondary side. So how do I transfer that? Very simple. First we have to find the turns ratio of the transformer, which we already have. It is a 5. I'm sorry. I'm going to put M1 and 2. What this means, once again, there is 5 turns of copper on the primary for every 1 turn of copper on the secondary. Remember we talked about that and I said, well, does it mean that it's only 5 and 1? Not necessarily. You can say 10, right, on one side. And then if it's 10 on one side, for me to to use the same turns ratio, then I want to have 2 on the secondary, right? So for every 10, if it's a 5 to 1, for every 10, I have 2, or 15, 3, and so on, right? So, but now, the A is, or the turns ratio is equal to N1 over N2, which in our case is equal to 5 divided by 1, or A is equal to 5, right? So that we know. Here. So how do we then transfer this impedance to the primary side of the transformer and deal only with the primary side of the transformer? Don't have to worry about any secondary. So we use the following formula. Z2 prime is equal to A squared times Z2. So A squared times Z2, which is given to us, right? And Z2 was equal to, was it 1 plus J4 ohms. Okay, so Z2 prime is equal to 5 squared times 1 plus J4. This is in ohms. Therefore, Z2 prime is equal to, let's see, I get 25 plus J100 ohms. Oh, okay. So we can then replace the circuit where we have primary and secondary of this ideal transformer into a more simple circuit as seen from the primary side, which basically looks like this. This is the 1 plus minus, and this is then R, oh, I'm sorry, I want to say R2 prime JX2 prime, and this total is Z 2 prime, which is equal to, once again, A squared times Z2, right? Once we transfer it. So then this looks like this. This we said was what, 25 ohms? And this is J100 ohms. This is then V1 plus minus. Basically, once again, all we're doing is taking the impedance or the load from the secondary side and transferring that to the primary side so that we can do all of the analysis on the primary side now without losing the power transfer. And we'll do one example like that, meaning the same amount of power, whether I do the analysis on the primary or the secondary, if it's an ideal transformer, it should be exactly the same, right? All right, so the next question was for a source of 1 volt. So what happens if I have 120 volts on the primary? 120 volts. What is my I1 current? I'm going to go to the other side. Very simple. Or we do solve that simple circuit. And that circuit is similar to the ones that we did even on the test. So that then becomes a circuit like this. Here's the load again. And they're saying I have 120 volts angle 0 degrees. That's going to be my V1, my source, and then this is going to be 25 ohms, 100 J100 ohms. So my current I1 becomes I1 phasor is equal to the voltage divided by, or V1 voltage divided by Z, this one, Z2 prime. It's not Z2, it's the impedance or the secondary as seen on the primary side, okay? So in this case, we have 120 volts angle 0 degrees divided by 25 plus J100. So then I1 gives us, I get 0.0 2A minus J 1.13. So you can convert this into, you can make this, you can convert that into a rectangular value, so it makes it easier. Let me see. Do I have it? No, I didn't do it. Basically, if you look at it, phasor diagrams like this, V1 is equal to 120 angle 0, and then we got a current somewhere here, right? I1, which is 0.28 minus J 1.13 amps, which makes sense, right? We have the current lagging the voltage by some angle, because it is a resistive inductive circuit, no purely inductive, no purely resistive, but a combination of. So that's it. That's pretty much the answer when you're dealing with ideal transformers. Let's do another example. Let me leave that there. So what if they ask the file?
I have a quick question.
Yes, sir.
It's about the that Z12 notation that just got taken away. It's from the primary of the second.
Oh, the V. Let me write it. Let me put it here. And I'm going to do one with the V just so that you see it right now. So you can think of the ideal transformer model being this. This is my transformer. You can think of that box. To the box, I attach a load, Z2. Across this load, there's V2 plus minus, okay? There is E, which is the EMF across the winding, 2 plus minus. There is an E1 plus minus, and there is voltage V1 plus minus. So really the question is this. Somebody's giving you that information, right? And they give you the impedance, they give you the load. And what they're asking you is, can you tell me what is the current on the primary side of the transformer? Okay? You can solve it here if you want, and then transfer that current to this side, and we'll do an example like that. Or what you can do is you can say, you know what? If what they're asking me is information on the primary voltage, the current of the primary, I'm not going to deal with the secondary. I don't care what's going on with the secondary. What they're asking me, let me give you an example. Say, for instance, somebody's telling you, hey, can you tell me there's current is going to flow here, E1. Can you tell me what type of conductor should I use to feed this transformer based on this load that I have? Oh, okay, so you're asking me not the wire where the load is connected. No, I'm asking you for the wire where the transformer is connected. Let me draw it this way. So here is the distribution line, A, B, C. And somebody says to you, hey, I have a transformer connected right here, and here's the transformer. Okay? And then I have, I'm going to call this X0, X1, and X2. And then I have a load connected to this transformer right here, Z2. This right here is the primary, the secondary of the transformer. You can think of that as V2. Do I make sense?
Yeah.
You can think of this right here, V1. This right here is where you connected the transformer from the primary side of the wires, right? And somebody's asking you, I want to know how big this conductor is. I'm going to use conductor as the example. I want to know how big that conductor is. For the load Z2 connected to it, could be a home, okay? Oh, what I'm really interested is, they're not asking me right now, which we could, they're not asking me for this wire. They're asking me for the wire on the primary of the transformer. So in order for me to know how big the wire should be, I should know the current. Current is how I size the wire, right? So with that being said, since I'm interested on the primary side, to make it easy on me, I want to transfer this impedance to the primary so that this model right here, an equivalent of it becomes like this. V1 I1 Z2 prime.
Okay, so it's just load Z2 after being converted to primary side.
Correct.
Okay.
Correct. The next example, I will show you that. The power, because this is an ideal transformer, I'm not losing any power, the power stays the same. Because the transformer right here, this box, is not accounting for any losses, right? So like you said, right, all I did is, oh man, I can do the analysis on the secondary side, but what would I do then? Maybe I should just make this circuit right here that has two windings, have to deal with I1, I2, V2. Well, forget about that. I'm just going to transfer everything to the primary because I'm interested in what's going on the primary side. Does that make sense, everybody? It could be. It could be that somebody says, well, no, I'm interested on the secondary. Okay, then you can do all the analysis on the secondary, right? And like I said, we'll do an example. But do I make sense of this? The beauty of the ideal transformer is whatever power you have here is the same as what you're inputting right here because you're not accounting for any type of losses incurred by the piece of equipment. Good. We'll do a few more, but
No, I got it.
you got it. Excellent. All right, so that's that. Where was I? What's that example number 2, right? There. Example number 2. Let me see. Did I do this move? I want. Okay. For the same example, actually, there's another question here. I'm going to erase this right here. So the next question is, okay, so now that you know this, next question is what will be the voltage on the secondary side of the transformer? Okay, well, let's see. Did I do this? Yes, okay. So next is move the voltage to the secondary, and find current I2 or move let me see, move the voltage to the secondary and find current I2 once you find 2, and move current I2 to the primary. Let's see. So let's go back to the example again. So I have the little transformer right here. I have this impedance, and this was 1 ohm, 4 j ohms, and then I need V2 plus minus. And I know that from what we found out is the voltage here was 120 angle 0 degrees. We can say that, right? That was the primary voltage. So what is the secondary voltage? Now, I use the same, I use the formulas with the turns ratio. So I'm going to say that V2 is equal to, phasor, is equal to N2 divided by N1 times V1. Okay, let's be careful right here. And write down the formula. I see this all the time. People often use N1 divided by N2. Remember, V1 is true, but V2 is N2 divided by N1. In other words, 1 over A times V1. That will give you V2. So if I know that the voltage across here, this transformer is 120 volt, there's no losses in voltage. What will that be on the secondary side? Well, what I'm going to do is V2 is equal to N2. N2 is 1, right? And N1 is 5 times, no squares, no nothing, just 1 over 5 times V1. V1 was 120 angle 0 degrees. Therefore, V2 is equal to 24 volts angle 0 degrees. Okay? So if I'm going to draw it here again. Basically what I have is this. Oops. What I have is this. There's the transformer winding primary. There's the transformer winding secondary. I know what I1 is. I know what V1 is, plus minus. I know what the impedance is again, right? That was 1 plus J4 ohms. I'm trying to find I2. I think V2 I already found, right? Using this, okay? So, same question. What if somebody says, well, I want you to tell me what is the current that is going to flow on this wire and this wire to supply that load on the secondary. Now, what I can do is I can just say I2 then, phasor, is equal to V2 phasor divided by the impedance Z2. Now I'm sitting on the secondary side, right? Make sense? Make sense? Everybody can? All right. So this is equal to 24 volts angle 0 degrees divided by 1 plus J10. Is that what I have? 1 plus J10. So I2, what do I get for I2? Is 1.411 minus J 5.647. So this is now the current here. So I know the current here on the primary, and I know the current on the secondary. Let me see where did I put the I1. I'm going to write here I1 phasor equals to, oh, did I solve I1, everybody?
J4, 1 plus J4.
Let me see. Yeah, I did, right? 0.28 minus.
You put 1 plus J10.
Did I do what? I'm sorry. Hold on 1 second. I'm just trying to see if I did I1. Yeah, I did. I'm sorry. It was 0.28
You put 1 plus J10.
minus 1 minus J 1.13. Is that what I have?
You put 1 plus J10.
I put 1, I'm sorry.
And the Z2 shouldn't be J4, not J10.
24.
For Z2.
Z2.
For I2.
Oh, I'm sorry. Did I? Hold on a second. Let me go back. What was the original value? No, Z2 was 1 plus J4, right?
We're saying
So you're saying you put 1 plus J10.
it's a given.
What?
It should be J.
J4, right?
Oh, I'm sorry. I see what you said. My bad. Yeah. Okay, so I have I1, I have I1, I have I2, I have V1, I have V2, and this is my impedance. This is the one that I was messing up. So I have two currents, right? Everybody sees current on the primary, current on the secondary, right? So what about this? So how much power am I consuming? Well, I can find the power, the apparent power, either from the secondary or the primary, and if I did everything right, the numbers should be the same, right? So let's try S or the power consumed by the load. So S1 is equal to V1 times I1 conjugate. Everybody agree with me? That's the formula, right? So I can say that S1 is equal to 120 volts angle 0 degrees times I1, which is converted I1 to polar form. You can put it right down there, doesn't really matter. I got for that 1.16 angle of 76 degrees. Okay, and why is this positive? Because I'm taking the conjugate, right? But the current was with the negative angle because it's lagging the voltage because it's an inductive resistive load. Make sense, everybody? All right. So if you plug that into your calculator, basically what you get is S1 equals 33.7, I think, plus J135. And this is in volt amperes, I'm sorry. Yeah, this is in volt, this is in amps. Okay, so that's the power consumed by the load. There's nothing consumed by the transformer. The transformer is ideal, has no losses. So everything here is going to the load. So you can say P1 is equal to 33.7 watts. JQ1 is equal to J135 bars, right? So that's the power if I am computing consumed by the load if I'm computing it from the primary side of the transformer. From the secondary side, I can say S2 is equal to V2 times I2 conjugate. So S2 is equal to, it was 24 angle 0 degrees, that's the voltage, times the current. I think I have 5.82 angle of 75 degrees, let's say. So then S2 is equal to 33.7 plus J 135. And this is in volt amperes. So P2 is equal to 33.7 watts. And JQ2 is equal to J135 amperes reactive bars. Okay? So I pretty much got the same answer, right? It doesn't really matter whether I'm looking at from the transfer of energy to the load, either from the primary or secondary, should be the same. You're not losing energy. This is, once again, it's an ideal transform. Any questions?
Bless you.
Bless you. All right. Let me do one more problem for an ideal transform. I'm going to erase this and I leave that on. So. This eraser is not very efficient. Okay, so example 2. A single phase transformer phase, I'm going to put ideal transformer rated at 20 kVA with 480 on the high side and 120 volts, of course, on the low side, and a load is connected to the secondary, of the transformer of 15 kVA at 0.8 power factor lagging. Okay, so basically what they're telling us is this. Here's the you have a transformer that is ideal. It says that the primary voltage rating is 480 volts, plus minus. The secondary rating of the transformer is 120 volts, okay, plus minus. So you can think of this right here once again. This is your transformer bus. And you have obviously an I1, we have an I2, and we're going to call this V1, and we're going to call this V2, okay? So connected to this transformer, there is load. And the load, oh, one thing that I forgot, this transformer is rated at 20 kVA. But the load is 15 kVA at 0.8? Yeah, power factor lagging. Lagging, did I write lagging? Yeah, okay. So, a couple of things that I want to mention on this problem. Before I start, there's two powers given. Or current powers for this problem. They're telling me this, they're giving this information and they're giving this information. When they tell you rated, the single phase transformer is rated at 220 kVA for 8120, this is what the transformer maximum capacity is. The rated is the maximum capacity, meaning that's what the transformer is being designed to run rated voltage and rated currents. That doesn't mean necessarily that you're going to connect a load that is exactly the same. The load will vary throughout the day, right? You can have a transformer that is 20 kVA. That doesn't mean that you're going to get your customer to pull 20 kVA all day long. They can be pulling less, or they can be pulling a little more load throughout the day. Now, less should not be a problem. You should be okay. Your transformer should be able to run without any issues. The problem becomes when the load increases above the rating of the transformer. Can you do that? The answer is yes. Companies do it every day. That being said, there's a limit that they give, and there's a period of time that you can do that, right? For instance, the transformer can be designed to run at 20 kVA, but you can also overload it by 5%, by 10% for a short period of time, and they usually tell you for how you can rate it. So continuously, you cannot go above 20 kVA. That's one. If it's less, well, things are good. Now, I give you this example. Transformers have been designed, obviously, to run below its rated value. And when they do not run, like in the summers when they actually get an overloading of the transformer, but they've been designed so that during the day you can be pulling more power, more current out of the transformer, but you're hoping that at night the transformer is going to cool off. It's a question of heat, right? Because if you're pulling more current, if you're putting more power out of the transformer, you're basically damaging, or you're eating the life of the transformer. I would say eating the life, not damaging it. So transformers, once again, they have a low profile, we call it that. Okay, you're gonna run maybe, I don't know, 110%, 120% for like 6 hours. But then I know that during the night, the load is gonna come down, and then you're gonna come down to maybe half of it in some cases, right? So you're giving the transformer a cooling period. And that's how system is designed, that you have that cooling period, and then you can extend the life of the transformer. The challenge that we have now is that transformers are actually being run either at its rated value or above, and they don't even have cooling period at night. And why? The reason is because, and the main reason, one of the main reason is electric vehicles. People come home and they charge the vehicle at night. So for where most of these transformers and the circuits were designed, now utilities are having, not just utilities, but utilities and other service providers are having to deal now with a transformer that is not cooling off, because the load demand continues to be the same throughout the 24-hour period. Do I make sense, everybody? So this is something I can bet you that some of you will be dealing with, especially if you work in distribution circuits. But back to the problem. The transformer is designed for that, but it's only being loaded by that much. Okay, so first question is, when we one more thing I forgot. The voltage here and the voltage here, that's what is what we call the rated voltage. Okay? That doesn't mean that the transformer is going to be precisely running at 480 and 120 on the secondary side. Case in point, that plug right there, that plug is rated for 120 volts. If you put your computer there, that's what it's rated for. But that's not necessarily what you're going to see if you go measure the voltage across the plug. It can be a little higher, it can be a little lower. If all the lights are on in the entire building, the voltage is going to be lower because there's high load demand. When we leave and we turn off lights, all the load comes down, then the voltage is going to run a little higher, right? What I'm trying to say is this just represents the turns ratio. This is what it's rated for. It doesn't mean necessarily that the voltage across here when the transformer is running is 120 volts. So with that, the question is, if, let's see, all right. When the transformer, sorry, let me close this, I don't want to address. When the voltage on the secondary is 118 angle 0 degrees, we're going to make that the reference volts. What is the voltage on the primary? What is the voltage on the primary? Okay, basically, once again, if the voltage across here is 118 volts, not 120, 118, what is the voltage on the primary side of the transformer? What is the utility providing you with at that point? All right, so say that then V2 is equal to 118 angle 0 degrees volts. And then we know that N1 is equal to 480, N2 is equal to 120, right? That's given to us. So I can say that A is equal to N1 divided by N2 which is equal to 480 divided by 120. That gives me a ratio of 4 to 1, 4 to 1, or 4, okay? So for every 4 turns of copper on the primary, I have 1 on the secondary. If you want to see it that way. Okay, so then I can say that V1 is equal to A times V2. So V1 then is equal to 4 times 118 angle 0 degrees, and this is in volts. So therefore V1 is equal to 472 angle of 0 degrees. This is in volts. So once again, what it's saying is, oh, whatever I have connected here is bringing the voltage to about 118 volts, okay? What is the utility side voltage of this transformer? What is, again, let me go here. This is not a good example, but let me try it anyway. Say, for instance, you have 480 volts rated, 120 volts rated, but when this is 118, what is the voltage here? Basically, it's 400 and, what did I say? It's 472, right? 472. That's what it's running on. Towards the end, I'm going to cover per units. Have I covered per unit with you guys, right? The per unit system? Okay. We'll talk about how to normalize these voltages. But for now, what all this problem is saying is, hey, I know whatever is connected is dragging the voltage down to 118. I want to know on the primary side, what is the voltage the utility is seeing right now? Okay? That's basically what the question is. All right, let me go back to this. All right, so that's this. The next question is, find the complex power. Oh, I don't want us to find the complex power. Let me erase this. Okay, find the complex power is to absorb by the load and the current I2 and current I2. Okay. So the load, we do know the power factor, right? That was given to us. So I'm going to call this theta 2, which is equal to the cosine inverse of power factor. So theta 2 then is equal to the cosine inverse of 0.8. And it's lagging, right? So theta 2 is equal to 36.87 degrees. Okay, so they gave us, we know the load, right? We know S magnitude, S2 magnitude is equal to 15,000 volt amperes, right? Or PA. Everybody okay with that? So, if I have that, then I can say that S2 is equal to 15,000 volt amperes at an angle of 36.87. And again, it's lagging. So I can say then that S2 is equal to V2 times I2 conjugate. Okay? I want to solve for this. I want to solve for I2. That's what they're asking me. I don't know what the current is being absorbed. So I can then do I2 conjugate is equal to V2 phasor divided by S2 magnitude, okay? S2, I'm sorry, not magnitude, S2. Okay, so I want to get rid of this conjugate, so I do a conjugate right here, that gets rid of it, but then this has now a conjugate. So I have I2 is equal to V2 divided by S2 conjugate, okay? You see what I did here, everybody? Or no? Remember, this is the formula. I'm solving for this I2, right? So I divide S, oh, I'm sorry. How come you guys didn't correct me? I made a mistake. This should be S2, I'm sorry. Divided by V2. Everybody okay with me now? Or not? V2. Everybody okay? You know what I'm doing, right? In order to get rid of the conjugate, I multiply by the conjugate. And so I do the same to the other side. So I end up with I2 phasor is equal to S2 divided by V2 conjugate. Okay, so I'm going to say then that I2 phasor is equal to 1,000, oh no, 15,000, I'm sorry, 1,000 volt amperes, I'm sorry, angle of minus 36.87 degrees divided by the voltage, which is 118 angle 0 degrees. Let me do it again. Let me say it again. Remember S2, this angle right here is positive, right? Here's negative because it's the conjugate. This is 0, so I don't have to do anything to it, right? This is the voltage across the load. Everybody agree with me? Yes, no? Right? I have this. I have a load right here of 15 kVA at 0.8 power factor lagging, okay? And they told me the voltage is 118, not 120, right? That's what the load sees across it, 118. So then the current, I2, then I2 should be, let's see. What do I get? What do I get? 7. I2 is equal to, sorry, 127.12. I don't know where I put this many numbers. 12 minus 36.87 degrees, and this is in amperes. So that's the current flowing here to the load. I2. Okay, the next question is find the load impedance. That would be C. Find the load impedance.
Professor,
Mm-hmm.
can you please how did you get S2 value with it? So 15,000?
Yeah, because it's 15 kVA, right? So 15 volt amperes. 15,000 volt amperes. Yes, no? Did I mess up?
No.
I'm good? All right. Okay, so let's see, where was I? Did I? 127, yep, okay. So it says find the load impedance, meaning the load impedance on the secondary side. On secondary of transformer. Of the transformer. So Z2 then is equal to V2 phasor divided by I2 phasor. So this is 118 angle 0, this is in volt, divided by 127.12 angle of minus 36.87 degrees, and this is in amps, therefore Z2 is equal to, let's see, 0.928 angle of 36.87 degrees, or Z2 in rectangular, which is my cheese here, is equal to 0.743 plus J 0.557, and this whole thing is in ohms. This is the resistance, and this is the reactance. Yes, sir.
Quick question. What's, can you repeat one more time what XFMR is?
Oh, transformer.
Oh, transformer.
It's just a type of transformer.
I'm sorry?
No, it's abbreviation.
Oh, yeah, I'm sorry.
You got lazy.
Wait, no, I don't even get lazy. A lot of us, when you go work for utilities, people don't write the whole word transformer, they just XFMR. It's just a abbreviation that we use, even on books. But when you're looking at, I don't know, somebody is telling you, hey, what is the XFMR? They're asking you, what is the transformer? So it's just a shortcut.
Okay.
Just transformer. Sorry about that.
I that was transformer.
I just, no, I just wrote it and I didn't explain that. All right, so that's the impedance. Now, what is the load impedance? So basically, it looks like this now, right? We have this transformer. We have 120, 0. We have 100 and this, oh, I'm sorry. What did we come up with that one? What was this transformer ratio? I'm sorry.
480, 120.
480 to 120, right? Okay,
Yes.
so this is 480. 480 to 120. Then we said, oh, well, but the voltage across here is actually 128. Is that what I said? Oh, no, 118, right?
118, yeah.
118 angle 0. So that's the voltage across the load. We know that now the load is, this is the resistance, this is the reactance, and they're asking us, hey, can you move that to the primary side? What will you do? I'm saying, okay, I know, on the secondary side, this is the impedance. What they're asking me now is, can you tell me what the impedance is? The equivalent impedance on the primary side, on the 480 side of the transformer. We just did it. Let's do it again. The formula for that is D, I'm going to say D. What is the load impedance? Load impedance seen as seen from the primary side, from the primary side. Okay, so we're going to call that Z2 prime, which is equal to A squared times Z2. So this is going to be Z2 prime is equal to 480 divided by 120, which is the turns ratio, squared, which was 4 to 1, right? Times Z2, which is 0.743 plus J 0.557, and this is in ohms. Actually, ohms, the whole thing is in ohms. Okay, and that gives me Z2 prime equals to 11.88 plus J 8.91. Say if you were to do this on MATLAB or Simulink, you have two circuits, potentially two circuits that you can draw, or you can use to solve MATLAB. The first one is going to be something like this. 118 angle 0 degrees, and this is Z2, which is equal to, where was I? 0.557 743 plus J 0.557. And this is I2, of course, this is V2, of course, or you can solve it this way. Z2 prime, which is equal to 11.88 plus J 8.91. This is V1 plus minus. This is I1. And I forgot what V1 was. Was it 472?
Yeah.
Right? So you can solve it as 472 angle 0. 472 angle 0, I'm going to say approximately. You can put this in Simulink, draw the circuit this way and this way if you're what you're after, by the way. If what you're after is the currents to the primary and secondary and the power, P, Q, and S. And because there is no losses, you should come up with the same values, right? You can double check those. I don't have it. Does this make sense, everybody? So ideal transformers are really easy. The only thing that you need to remember is the only thing you need to not remember, but to have is how do you transfer from primary to secondary voltages and currents. Let me see. 127. Can somebody tell me what the I1 was? What was the value for I1? Did I solve that? I didn't solve it.
No.
I didn't solve it. Okay. What I was going to do is this. You can find it. I already gave you the formulas. In this problem, magnitude-wise, will you expect current I1, you know I2, will you expect current I1 to be larger magnitude-wise? Don't even think about the angle for now. Just the magnitude of the current. Are you expecting the current I1 to be lower or higher than I2? Lower. Okay, the higher the voltage, the lower the current and vice versa. Okay, so with that, remember we talked about it, what that turns into is the conductors that you're using, right? So on the primary, for the same rating, obviously the conductors on the primary are going to be a little thicker than the, on the secondary are going to be a little thicker than the ones on the primary. But the spacing in between the terminals on the high side is larger, was you need more spacing on the high side than you need on the low side. Make sense? Okay. All right. So this is ideal transformers. As I said, I'll build a couple of circuits on MATLAB, and I'll give them to you so that you can probably play around with them. Now, life is not that good, right? And simple. This is just a way to do some estimation analysis, meaning there's some error that we're incurring using this transformer model, the ideal transformer model. Because what we're saying is, oh no, the transformer is perfect. Transformer doesn't have any issues. The flux is 100% contained on the core. The wire that we're using, the copper wire, we're not using copper, we're using gold. Gold is a super good. Has a very low impedance, right? But who is going to build? If there's still copper from substations, can you imagine if it was gold? That is an issue, by the way. Big issue on electric utilities or electrical infrastructure. Copper theft is a big problem because copper is very expensive. So the utilities especially have issues with their groundings because their groundings they use copper, they bury copper, so people will come and cut it and try to pull it out and will sell it. So copper theft is a big problem. All right. What about the next thing? Non-ideal transformers. transformers. Equivalent circuit. And by the way, the non-ideal transformer equivalent circuit still is not the most accurate model. You can continue, I'm sorry, just getting hot, it was cold outside, but now it's hot. You can, a transformer, there's just so many things, and I was showing you going on, there's that the models that we utilize, the ideal and the non-ideal, we still make a lot of assumptions on both of them. But the non-ideal, probably for steady state analysis, where you're really, really concerned about not only the losses, but you're also concerned about sizing wire, making sure they use the right wires to connect the device, is good enough. But if you're doing analysis that is probably, if you're doing analysis that is more to just the ideal, but a transient, especially electromagnetic transient, the ideal transformer model, it doesn't really work because it doesn't account for the capacitance of the transformer. There's capacitance on the bushing. There is capacitance, internal capacitance on the core. There is capacitance on the winding. But the capacitance on the winding, capacitance on the core, and the capacitance on the bushing is so small in comparison to the inductance and the resistance that for steady state analysis, we pretty much say, it doesn't exist. But point I'm trying to make is this is not the only model that you can continue to refine the model depending on the type of studies that you do. So non-ideal transformer, obviously we have the same thing, we have a core and a winding. We'll call this P1 plus minus, then we have a secondary P2 plus minus, and right here there's an E1 plus minus, E2 plus minus, meaning the voltage or the EMF across the cord, or the winding on the cord, okay? And then we have the terminal voltages V1 and V2. We're gonna say there is number of turns N1, and of course number of turns N2. I1 and I2. So V1 then again, phasor is primary voltage. I1 of course is primary current. We'll talk about this already with the ideal transformer current. V2 is secondary voltage. I2 secondary current. Then we have N1, which is turns, number of turns on primary. And then 2, number of turns on secondary. Okay, nothing changes from ideal transformer as far as the nomenclature. And then you can say E1, I'm going to put it up here. E1 is the EMF cross winding. And then E2 is EMF, electromagnetic force across. Is it 2 C's across? What's 1 C? Winding 2. I should know. Okay. Now, but the difference between the ideal transformer and a non-ideal transformer Following. I'm gonna put it as, put it as a series, I'll put it as a part of the branch later. Um, E1, E2 plus minus. Okay, this right here. This is what we just talked about. This is the ideal transformer model. This thing here is what we just talked about. Non-ideal transformer, on the other hand, has to account for the transformer losses. So we're gonna have this R1, JX1. We're gonna call this R, M, X, M, JXM. We're gonna call this R2, JX2, V2 plus minus, V1 plus minus. This is I1, this is I2. Okay, so to the ideal transformer, we added this and we added that. So we added these impedances and those impedances. They were those impedances represented. Let me write that down. Okay. Did I write everything? Yeah. Oh, forgot one thing. N1, N2, turns ratios. Okay, so R1 is the copper losses. Of primary winding. Okay, JX1 is the leakage losses of primary. Remember we kind of talked about that just a little bit when we were talking about electromagnetics, and I said the leakage, the flux, right? Remember we said, oh yeah, there's a flux here, and in the ideal transformer, what we're saying is the flux lines, they stay within the core. No flux lines go outside the core. They all are confined, but the reality is that there will be some flux lines that are flowing in air. You know what I mean? So some of those flux lines feed, right? Some of those will leak to air, and they become those reactive losses of the from the primary winding, or caused by the primary winding. So that's what I was telling. Remember when I was telling you the importance of having for the transformer core to have a really good geometry, like that you really maintain a very, very detailed, an ideal geometry so that you can capture most of the flux. Is it possible for it? No, there's no such a thing, right? You're always going to have. But that geometry, once again, the manufacturing of it, if you cannot manage it, then it will turn into reactive losses, which is not what the customer wants. Okay, so that's part of the design. That's part of how precise the design is. Okay, so R2 is copper. So this is the conductor, right? The copper winding. Losses of secondary winding. JX2 is the leakage losses of secondary winding. Okay? And then we'll call this Z1 is equal to R1 plus JX1. This is the primary impedance, refer this to the primary impedance of the transformer. Z2, which is equal to R2 plus JX2, is the secondary impedance. And the name, you'll hear this name, or you hear this term, leakage impedance. That's what, when somebody tells what is the leakage impedance of the transformer, they're talking about the R plus the JX. And we'll get to a point where we actually combine this. So when the manufacturer of transformer gives you this information, they give you this information. They will not give it to you as separate R1, R2, JX1, and JX2. They give it to you as a combined value. We call that the equivalent leakage impedance of the transformer. We'll talk about that. Okay, so there is another branch right here. Ooh. RM and XM. What is that? RM is the we call them core losses equivalent, resistance, and then XM or JXM, let's say XM, is the magnetizing let me see, magnetizing reactance. Oh, transformer. Okay. Let's take a look at this one. RM represents the magnetizing, ing, I'm sorry, magnetizing losses, which are, yes, remember we're talking about the core of the transformer. We use the transformer core. I'm not talking about windings, right? Just the core. And then we remember we talk about slicing it. What is it that we're trying to reduce? The eddy currents, right? There's like this little, we talked about this little vortex, right? That develop here. Oh, okay. So that's one. Losses which are are due to eddy currents. And what other losses we had on the core? And we have the eddy current losses and the hysteresis losses, right? So keeping those what do you call it, the lamination as thin as possible is going to reduce this RM, right? How do we manage the hysteresis? By the material that we use. So the better quality the use of material, the less your your hysteresis losses, and remember, I think I mentioned this, if I didn't, I'm sorry. And I said the area inside this curve is what we call those losses, right? So what you want to keep is that hysteresis as thin as possible. The larger the hysteresis, the more losses you have, the higher the RM will be. And then let me see, and the XM as well. Now, let me say this. For the most part, actually not for the most part, even on the exam, on the exam, on the homework, open just about any book, and you'll see all of the problems. We often neglect that. We often, because it only comes into play when you energize the transformer for the first time. And we're not talking about transformer energization. That's not what this course is about. The course here is how do we account for losses due to a transformer in steady state conditions. That's what we're about. It happens that this branches, if you look, this is the current going out of this source, and if things are good, all that current is going to make it here to produce a current on the secondary. But do you see that there is I1 comes in here, but that's not it, all the current going to the actual the winding of the core. You see there's some current going right here. I'm going to call it IP. That's the magnetization current. And the magnetization current is so small, and that's why you want its magnetizing current to be so small that it doesn't impair, or most of your current from the primary goes or is reflected on the secondary. Okay, so that's something once again that it has to do with the quality of your transformer, the quality of the material. On very large transformers, it's a little easier to manage because we're talking about a lot of material. There's a lot of things we can do. Where this becomes a little bit of a problem is not on power transformer, but on instrumentation transformers, on CTs and VTs. They're transformers, right? They're just for different purposes. Because once again, the current starts a lot smaller that the magnetizing branch can make a big difference on the secondary current. Because not all of the current gets induced to the secondary. But for us, we're gonna say we know that it exists. We also know why it's there. But we're going the problems that we're going to solve, or that you tend to solve, you often leave this out and you ignore your magnetizing branch. There's another way to draw that, and we'll do it another way. But for now, let's just leave it like that. Oh, no, let me do it. I have here. Same thing, equivalent. R1, JX1. Oh, I can also draw that branch like this. As a parallel combination, I'm going to call this RC. This is XM. And here's my winding, my ideal transformer part. And then R2 and JX2, R1 and JX1. The only thing that I changed is I made this series branch, I converted it into a parallel branch. I'm going to call this IP. I'm going to call this IR. I'm going to call it IM. So IP, this 2 plus that is the excitation, what we call the excitation current of the transformer. But again, under ideal conditions, that impedance is really high in comparison to the primary and secondary windings, that for all practical purposes, there is an open circuit there. Let's see. Yeah, okay. So, similarly to an ideal transformer, sometimes we're asked to draw an equivalent circuit as seen from the transformer primary and transformer secondary. Just like the ideal transformer, it makes it so much easier when it comes to analysis, especially if you're doing analysis by hand. If you're doing it on the computer, it doesn't really matter. Because once again, the computer is going to do all of this for you. But let's start with the transformer. Equivalent circuit. Refer to the primary. Okay. Again, we have this. RC, XM, XM, R1, JX1, sorry, JX1. And here's my field transformer again. Field transformer. And then I have R2 and JX2. And then I have E1 plus minus, E2 plus minus. I'm going to have I2. And out here, I1, V1 plus minus. Yeah, I got everything. Okay, so the A for the turns ratio. Here's N1 and 2. Again, not the change. A is equal to N1 divided by N2. Okay, so now what we're trying to do is how can we move the secondary impedances from the primary side to an equivalent that absorbs the same amount of energy on the primary side of the transformer. Okay, use very similar, if not same formulas that we did already for the ideal transformer, except that now we're talking about, this is not the load. Remember, this is the entire thing is the transformer non-ideal, okay? Except that once again, now we are accounting for its losses. Not everything that comes in necessarily comes out. Okay, so let's start with X. R2 prime is equal to A squared times R2. A squared, the turns ratio squared. X2, JX2 prime is equal to A squared times JX2. Okay? Let's see. Or you can say again, R2 prime is equal to N1 divided by N2 squared times R2. That's another way to write it. And JX2 prime is equal to N1 divided by N2 squared times JX2. Okay, so once again, we're taking this impedance and we're moving it as an equivalent circuit with the same amount of losses to the primary side, so we don't have to deal with the secondary side any longer, just like we deal with the ideal transformer. That will make it easier for us to do analysis. So what we have then is this. R1, JX1, R2 prime, JX2 prime, and then now we can call this V2 prime plus minus. And this is still our C and XM, JXM, your magnetizing branch. So again, we're moving all of that impedance to the primary side, and we end up with a circuit equivalent of the transformer on the primary winding voltage level, okay? Oh, yeah, just a note, I use the word primary and secondary. Does it mean that primary is the high voltage and the secondary is the low voltage? No, not necessarily. Primary means where the source is connected. Secondary means where the load is connected. Okay? So, transformers that we see around here on the poles, serving customers, they're for the most part step-down transformers, so the primary is a high voltage. But if you go to a power station, it's the other way around. The source is on the low side and the line is, or the load is on the high side. So primary only means where the source is connected, okay? It doesn't mean high, although high, of course, means high voltage, low means low voltage, but that's how we define primary and secondary. Okay, so what about V? So this is V1 plus minus. This is V2 prime. V2 prime is equal to N1 divided by N2 times V2, okay? So basically what we're doing is we're taking this voltage here, V2 plus minus, and we're moving it to the secondary side, to the primary side of the transformer. And the magnetizing branch, doesn't really matter where the magnetizing branch is. And I tell you what that doesn't really matter, what I mean by that. So one more step for this transformer. We're gonna say that R EQ is equal to R1 plus R2 prime. JX EQ is equal to JX1 plus JX2 prime. Let me draw it here. REQ JXEQ V2 prime plus minus V1 plus minus RC JXM. Okay, so basically what we have done, we have combined the resistances and the reactances of the transformers as seen from the primary side of the transformer. Okay, now here's the piece that I was going to tell you. When you go look at a transformer nameplate, or when somebody gives you the transformer reactance, okay, they will give you the equivalent value, meaning the addition of the primary and the secondary resistance and reactances. They never give you the values as separate values. Okay. Now, are there any times or reasons why you want to have the primary and the secondary separated from each other? Yeah, if you're maybe doing, or you're trying to account for the losses of the primary and secondary winding as a separate, not the entire transformer, then maybe you can do that. A rule of thumb, this is not exactly, doesn't necessarily work that way all the time, but it's a good assumption. You can always say the total. Say, for instance, they tell you, okay, the equivalent resistance of that transformer is 10 ohms. Okay, you can say that then there's 5 and 5. You can split it half and half. Same here, half and half. Okay, obviously you're going to have to transfer it to the secondary if you want a full-blown model, right? And we'll talk about that. But the point I'm trying to make is when you get transformer data, you go to a nameplate of the transformer and they tell you the X of the transformer. Sometimes they don't even put EQ, they just say X equals boom value. Basically what they give you is the combination of the two primary and secondary windings. Does that make sense, everybody? Okay. If you, for whatever reason, the model that you're building, they tell you no, you gotta give it both Sometimes the manufacturer might give you the value. Sometimes they might say, oh, we don't have it. Okay, I gotta do analysis, split it in two, that's good enough. We'll talk more details about it. All right, so here it is. We can also further reduce this model. Oh, yeah, this is what I was gonna say. You can leave this branch here in front of the equivalent resistance and reactance, or you can move it on the other side. It doesn't make any difference. As a matter of fact, the final model that you're going to be using for the most part is this. V1 plus minus V2 prime plus minus REQ JXEQ. And then, yeah, I'm gonna say I1 for now. I1 and I2 prime are the same. Oh, V2 prime, not V2, V2 prime. That's the model, once again, that usually you have on computer programs like ETAP or PSLF, PSSC, or Simulink. That's the model. There is a way, even on Simulink, and maybe I'll show you that next time I'll build the model. There's a way to ignore this branch, and I believe, if I'm not mistaken, when you put a transformer model on Simulink, there's a checkbox. If you check the box, it accounts for this branch. If you check the box, it drops that branch. As I said, this is the actual model that we're after. So this is the equivalent circuit for a transformer as seen from the primary side. Okay? I'm gonna leave it here. We'll come back to it, to some examples. All right, what if the question is, hey, no, I want the equivalent of a transformer, but not seen from the primary, actually seen from the secondary side. I shouldn't erase this. What do you think we're gonna do? Any ideas? Any guesses from what we have been doing so far, even with the ideal transformer? How do you think we're gonna treat the impedances of the transformer core and windings in order to transfer them from, now we're gonna transfer from the primary side, everything to the secondary side. What do you think you're gonna multiply by? You transfer from the secondary to the primary, multiply by A squared. To transfer from the primary to the secondary, what do you think? 1 over A squared. It's the inverse of that, right? So, let me see. For today, that's why I said I should erase the secondary. Again, same thing. Impedances, excitation branch, R1, JX1, V1 plus minus I1. Oh, by the way, yes, the other thing, you'll see it on the books, and I don't know if I put on the homework, there's 2 dots right here. That means that what the dots mean is what we refer to it as the transformer polarity. Okay? What we're saying is that from the primary, the current is going in this direction, and in the secondary going in this direction. So out of the dot, out of the dot. Why does it matter? It matters because of this. I'm just going to do one winding. I start from the top, over, under, over, under, over, under. On the secondary side, over, under. I'm sorry, over, under, okay? So, if you look, both primary winding and secondary windings start right on the top of the cord, outside right on the top of the cord. That is this polarity marks, that's what that means. This is a lot different. if the transformer is built this way, over, under, over, oops, I'm gonna do one more. Over, under, and then over. If I go under, then over, and then under, and then over, you see the way the transformer winding, or how is the copper wires one goes over this top of the cord, but in the secondary, it comes under on the other side of the cord. In that case, you'll see this like that. So if you see this here, that means that that's a polarity, transformer polarity, and that is a big deal. We'll talk about it when we talk about three-phase transformers, okay? Because the current here is gonna induce a current in this direction with different angle, phase angle. So that's what that means. If you see those two dots, that means that this is how the transformer is built, and that's probably 95% of the time. That's how we want it. If you, as I said, especially in three-winding transformers, if you don't pay attention to that, if somebody tells you, hey, I want you to wire 3 single-phase transformers and make me a 3-phase transformer, and you're not careful with those polarities, you can actually blow out the transformer. Because when the transformer is supposed to be on the peak, it's on the other side, so you can have this potential difference between, and hence you can have a short circuit. But these dots right here are not just there because R1, R2 on R2, JX2. Okay, so the question now is, how can I take this information or that winding and make an equivalent with the same amount of energy absorbed on the secondary side of it? So that would go R1 prime, which is equal to 1 over A squared times R1, okay? When I transfer this, JX1 prime, and you can write, well, let's just leave it at that. R1 prime and JX1 prime is equal to 1 over A squared JX1. Here's R, C, and XM. You can transfer this branch to the secondary side the same way, 1 over A2, but for the most part, the magnetizing branch is often left on this side, and because we are going to be working on steady state analysis, we're going to be ignoring that, so it doesn't really matter. But you could, if somebody tells you, hey, can you transfer the excitation branch to the secondary side? Sure. All you do is you multiply those values by 1 over A2, and then you transfer it the same way you did with the primary resistance and reactance. So then what we have here is a transformer equivalent circuit now, as seen on the secondary. I'm gonna do it here. Again, I'm leaving the magnetizing branch on the primary side. I'm not moving it. V1 plus minus. This is my ideal transformer piece. My polarity marks. N1, N2. Now I have R2, JX2, R1 prime, JX1 prime, and I have V2 plus minus, and then E2 plus minus, E1 plus minus. I'm going to say this is I1, and then the current here is I2. So I can write this as follows. R equivalent secondary, that stands for secondary, is equal to R2 plus R1 prime. JX equivalent secondary is equal to JX2 plus JX1 primary. Okay? I'm sorry, I'm gonna write it. I'm gonna do it here, still have room. So you can write the equivalent secondary as follows. We're gonna ignore the multi-Tyson branch, and we're gonna say that the equivalent circuit now, as seen from the secondary, this is R EQ secondary and JX EQ secondary. And here's my V2 plus minus. This will be V1 prime. We'll talk about this. And that will be the equivalent circuit as seen from the secondary side. So for the most part, and I'm not saying always, but for the most part, most examples that you come across are usually done on the primary side of the transformer. Because you want to transfer everything to 1 volt. You always want to transfer everything to 1 voltage level, assuming that you're dealing with step-down transformers. Okay, different would be if you're dealing with step-up transformer, then you might have to then use the secondary side. But for now, any questions about how to come up with the formula? So they're very simple, right? Remember, if you're transferring secondary windings to the primary side, you multiply by A squared, or the translation square. If you're transferring primary values to the secondary, you divide it by 1, you multiply by 1 over A squared, or N2 divided by N1, same thing, right? Make sense? Or did I confuse you when I said that? Okay.
Yeah.
Makes sense. All right. Any questions? So let's do a quick example. Well, not one example. Let's do a few examples. Let's start with this one. Okay. If we're given the following model, R1, JX1, this is 0.72 ohms, J 0.92 ohms, and I have my Tyson branch here. This is 632 ohms, that's RC. And XM is equal to J 4,370 ohms. And I have, okay, be careful on this one, R2 prime, JX2 prime. This one is 0.7 ohms. This is J 0.9 ohms. Okay, so this is the transformer model, V1 plus minus. I'm gonna write this, V2 prime plus minus. So the question is how to develop a transformer model. Somebody gives you this, and they ask you, hey, can you give me the transformer model with equivalent impedance ZEQ? ZEQ is equal to REQ plus JXEQ that I can put into my computer, MATLAB, okay? Or PSSC or PSLF or PowerWord. Simple. We are, all of those impedances that you have, on that model given are both as referred to the primary side of the transformer. Do I have to do anything to it to get the equivalent circuit? Or the REQ and JXEQ? Do I have to do anything? You have to manipulate those numbers in any way. Yes, no? What would you do? I'm after this value, so I can have a transformer model that would look like this. So I can enter this into my software tool, whatever I'm using.
You have to transfer, no? Or I combine?
Just combine,
Yeah,
right? Be careful, you don't have to do anything. You don't have,
combine.
all the information is already given to you. Whoever gave you this information is given to you as referred to the primary side of the
Oh.
transformer. Okay? It's already been transferred for you. By the way, you can kind of tell. You can kind of tell if you're not sure, you just look at the numbers. Look at the impedances. They're very much the same. Remember I said this to you?
Oh, yeah.
I said, oh, if somebody tells you, hey, listen, can you give me the transformer equivalent circuit, but can you give me the primary and the secondary impedances of that transformer? It doesn't matter what refer to the primary, secondary. And they said, I don't have that, I don't know. And you come across even transformer manufacturers, sometimes they don't even want to go talk to the transformer designer. They're in Paris or whatever, and you call them, and it's happened to me, I said that, and they go, I don't have that, no, we don't do that. What do you do that? You do that. You test the transformer, I know you do that. But because they're not used to it, most manufacturers, they just give you those values. The designer, the guy who's actually designed the transformer and doing the testing, they have that information. That's to make it to you. What can you do? Well, you can just divide it by 2. So simple. All you need to do here is REQ is equal to 0.7, is it 272 ohms plus 0.7 ohms. So that's equal to 1.42 ohms. And JXEQ is equal to 92 ohms plus 0.9 ohms, and that gives me, oh, this is J, by the way, I'm sorry, J. Let's see, J is equal to 1.82 ohms. So my transformer model, I'm gonna ignore, you see how large the impedance on the magnetizing branches in comparison to this? So most of the current is gonna flow this direction. It's gonna be a tiny money current. When we talk about how do we measure that? How do we measure that? How do we determine those values if we do not know, but we do have a way to do this testing in the lab? How do I measure these values and these values? I just have the box. I go to the manufacturer says to me, oh, most important, you call the manufacturer and it says, oh yeah, this company was closed in the year 2000. That doesn't exist anymore. There's a lot of companies that don't exist anymore. You end up with equipment, whether you work for a consultant or you work at a factory or you work at a utility. Yeah, I don't know, Trident doesn't exist anymore. Or Schneider, oh, they don't make transformers anymore. So where in the heck do I get this information? We did a lab last week, right? For the machines.
Mm-hmm.
And we were trying to find the impedances of an induction machine. I'm sorry, of synchronous machine.
Synchronous.
Okay? So you can determine these values, these resistances, these reactances, by test. All you need is a nice voltmeter or voltage source and a good, well-calibrated multimeter that can measure current, voltage, real, and reactive power. And then you can come up with this value. So we'll do that. The point, what I'm trying to make is that there's multiple ways for you to obtain this kind of information. Most important, if they tell you, you cannot do that on the transformer. Are you kidding me? Put it out of service and you're gonna do your test. They don't trust you, even though you know what to do. Your boss will say, oh, I'm not gonna let you do that, right? How else can you get that information if nobody can give it to you? But you need to put that information on your short circuit analysis or your motor steering or your low flow analysis. You need those impedances. There is such a thing as generic values, and I'll give you a table of generic values that you can use. The problem with generic values is that they're generic values, right? So they're not as accurate, but in some cases good enough for the analysis that you're doing. So either you get it from the manufacturer or you have to go do some testing in the lab. By the way, this is the only lab that we don't do here. I don't know why, but maybe because we just don't have enough transformers in the lab. But we do it on the synchronous machine and in the induction machine. So we'll talk about that. But once again, let me just repeat this. I1, hopefully it will go straight through this branch and very little will be here so that we can neglect this. As I said, you can look at the numbers, very high. So this is an open circuit for practical purposes, right? That's why it behaves like that. Okay, so then this is 1.42 ohms, J 1.82 ohms. And this is what you will, this is the information that you will put in the software. Okay, that was very simple, just so that, you know, but it comes around. Okay, example number 2. Number 2, given the following, transformer data. Okay, R1 is equal to 0.5 ohms. JX1 is equal to J2.0 ohms. R2 is equal to 0.005 ohms. JX2 is equal to J0.2 ohms. High voltage side is 2300 volts. Low voltage side is 240 volts. The rating of this transformer is rated for 75 kVA, kilovolt amperes. The frequency, of course, 60 hertz. Doesn't matter, of course it matters. Transformer is being designed for that. Put 60 hertz. And then we're going to say here, neglect the magnetizing branch of the transformer. So, question number 1, find the transformer circuit equivalent as seen from primary. B, find the transformer circuit equivalent as seen from secondary. And then C, find the voltage V1, and this is transformer terminals, primary terminals. If the transformer is supplying IG rated load. This is a key word. Rated load at 0.85 power factor lagging at 240 volts. Okay. So first, find the equivalent circuit on the primary, as seen on the primary, find the equivalent circuit as seen on the secondary, and then last, find the voltage V1 or terminal of the transformer when you are supplying a rated load at 0.8 power factor lagging at 240 volts. So the load, we know the load is going to be on the secondary of the transformer, right? It's 240 volts. Rated load, they give me power factor, but not telling me how big the load is. What is the transformer rated for? Anybody? From the data that I gave you, what is the transformer rated for? What is the transformer capacity?
75 kV.
75 kVA. That's the rated capacity. When somebody tells you you're connecting rated load, rated to the transformer, what they're telling you is a 1-to-1. The load is as much as the transformer. So the transformer is running at full capacity. That's basically what kind of sort of they're telling you with this. When they tell you rated load, they don't tell you anything else. All right. So let's start with A. So let's draw the transformer equivalent circuit. All right. Okay, exercise. Okay, so it looks like this. Just the transformer itself. Remember, they told us to neglect the binding wire, so we don't have anything. So this is 0.5 ohms. This is J2 ohms. This is 0.005 ohms. And X is equal to J0.02 ohms. Okay. And this is, of course, V1 plus minus, V2 plus minus, E2 plus minus, E1 plus minus, okay, and then the turns ratio, N1 and 2, they tell us the turns ratio is 2300 to 240. Okay, so that's the turns ratio of the transformer. For every 2,300 turns, there is 240 turns on this side. Okay, so we can use the voltage, right, for that. All right. First step first, let's do this. A is equal to N1 divided by N2, which is equal to 2300 divided by 240 equals to 9.58 approximately. Okay, that's the transfer ratio. So we're gonna transfer this, we're gonna transfer this to that side. So I'm gonna say that R2 prime is equal to A squared times R2, which is equal to 9.58 squared times 0.005 ohms. So R2 prime is equal to 0.46 ohms, okay? JX2 prime is equal to A squared times JX2, which is equal also to 9.58 squared times J 0.02 ohms, and then JX2 prime is equal to J is 1.84 ohms. Okay, so I have R2, JX2. Now, I'm going to draw the equivalent circuit as seen from the primary. R1, JX1, R2 prime, JX2 prime. Again, this was 0.5 ohms. And J2.0 ohms. And this one right here is 0.46 ohms. And this right here was J1.84 ohms. Okay, V1 plus minus, we can say V2 prime plus minus. Okay, then this and this and this and this we're going to combine, so we're going to say REQ is equal to R1 plus R2 prime, which is equal to 0.5 ohms plus 0.46 ohms, and that's 0.96, right? So REQ is equal to 0.96 ohms. Okay, so that JXEQ is equal to JX1 plus JX2 prime, and that is equal to J2.0 plus J1.84. So JXEQ is equal to 3.84, J3.84 ohms. Okay, so my equivalent circuit then is I'm gonna come back to this too. So the answer for this one is, we can get it this way. REQ, JXEQ, what is it, 0.96 ohms, J 3.84 ohms, okay, V1 plus minus V2 prime plus minus 4. I mean, you can also do it this way. It doesn't really, it's a big difference. What they're asking you is for the equivalent circuit. You can do it this way. V2 plus minus. You can need the secondary, but there's nothing on the secondary, right? There's no winding. We transfer everything to the primary, so we let this side here empty. So this is REQ, JXEQ, same values. V1 plus 1. This is not V2 prime, this is V2, meaning I still have it in 1 and in 2. Okay, So either one, somebody asking for the equivalent circuit, either one is correct. Okay? Any questions? Very simple, right? I'm gonna say it again. I'm repeating myself. Somebody says, oh, by the way, they should give you this value. Sometimes they don't even give you that. Oh, here is the transformer impedance. And like I said, I'm gonna say 95% of the time, they give you that impedance the same from the primary. And they just give you X equivalent and RE equivalent. And I'm gonna say again, and then you say, hey, whatever analysis that I'm doing, I wanna represent the two windings as separate, not as one, but as separate. So, but the information they're giving me the lumped value. All you do is you take this, divide by 2, right? Divide by 2, divide by 2. Make sense? You leave half here, and then you transfer the other half to the other side. But when you transfer it to the other side, what you're going to do? You're going to multiply it by what? 1 over
A
squared. Do I make sense? In other words, I'm going in the other direction. I'm going from there to this direction. Okay? The numbers were, it happened to be this example. They were very, almost half of each other. In real life, and they like literally half and half. They try, but they cannot keep it half and half, right? I mean, the manufacturer will try, but there's always going to be a difference. And they do that measurement. There's equipment. There's equipment that is used. Utilities actually use it because, oh yeah, that's the other thing I was going to say. On small distribution pole mounted transformers, do you think the utility is going to spend money? How many do you think they have? I'll give you a number. Southern California has about approximately 37,000 distribution circuits. How many transformers per distribution circuit? I'm going to say average 20, 30. How many transformers do you think they have? They have a lot of distribution transformers. Lots of them. Do you think every once in a while they do maintenance on those transformers? No. I think I said this. Maybe some of you were not here, but I say it again. We used to make the joke that somebody came one time and said, so how do you know when to replace the distribution transformer? How do you utilities decide like, okay, it's time to go get the transformer and put a new one? When they blow up. I said that last week, right? When the transformer blow up, okay, we're gonna go and put a new transformer. You can walk around, especially if you go in areas like the coastline. If you go anything near the coastline and you see poles near the ocean and you see rusting on the transformer, on this whatever, on the casing of the transformer, coastlines is bad. What do you have in the air? Moisture, yes, but there's somebody said the other word. Salt. Salt is so bad. It's corrosive, right? So depending on where you are, and California, just California, Southern California, happens to be so many different climates that we have. We have salty, we have desert, we have mountains. So the climate, by the way, it affects these things. It affects this device. So, but this distribution transformer, they blow up, they put a new one. That's how they maintain it. It's just by replacing them. There's no way you can get them to do that. When you're talking about very large power transformers inside the substation, that's a whole different deal. There's a maintenance cycle that utilities have. It used to be 5 years, but just recently somebody said, no, we're doing 10 years now. Meaning every 10 years, there's a crew that's all they do. They will come and say, all right, let's go look at this transformer at this substation and let's make sure that they still good. So they do testing, and what they do testing, basically they go and measure these values. That's one of them. They measure these values. They have equipment, they plug it in, boom, and it gives you the transform. Actually, it gives you this value, and this value. It also it can give you the hysteresis, because the hysteresis can tell you a lot. Hot spots. There's a lot of stuff, but there is some maintenance associated with those, because you're talking about at least how many 500 kV substations to 30 in Southern California Edison. I'm gonna guesstimate. I used to that. I'm gonna say 15 substations that go from 500 to 230 kV. About 15 in the entire Southern California Edison. There's 4 banks per substation. Do the math. There's not that many, right? But that transformer, if it fails, it's a lot of money. So you gotta, yes, sir.
So you just order a new transformer.
No. By the way, that's a very good question. Distribution transformer, that's the other thing. Distribution transformer, you can order, fails, you order. No. They order on bulk. And then you go to, if you drive around, you'll see it. Drive around and you see a substation. Sometimes you see a fence and you see a bunch of transformers just sitting there. They buy bulks because they can all, they have to have, it's a reoccurring equipment, like it's moving. Every day there's a transformer, one transformers that fail. So no, you cannot do that. They order, they do a forecasting. Edison was getting, PG&E Edison, PG&E Edison and San Diego Gas and Electric, they were getting hammered by the PUC on that. Because the Public Utilities Commission used to say, how do I know that, first of all, how do I know that you guys have enough transformers in case of emergency? Number one. Number two, with all these wildfires, how do I know that you guys have replaced old transformers? So they were pushing on the utilities to do, in high fire risk areas, to do what I said, proactive replacement of transformers. But that's a big deal for a utility, because that's not money that they don't want to spend that money. They don't want to spend the money until they need to spend the money. Do I make sense, everybody? So to Weston, they do a forecast. And this year, this is what the fleet looks like. And this is what we anticipate this many transformers might need to be ordered. And they order a lot. So, like I said, the other transformer is a whole different, we'll talk about that. Any questions about this? This is simple, right? All you need to remember is the formula. Now, what about the other way around? What if I want to transfer the impedance? I want to transfer this impedance to that side. Okay, I'm going to erase this. I'm going to erase this. So I'm going to take this once again. Transfer is secondary. So with that one, we're going to say A doesn't change. Same turns ratio, 9.58. And R1 prime is equal to 1 over A squared times R1. So R1 prime is equal to 1 over 9.58 squared times 0.5. R1 prime is equal to 0.0054 ohms. Jx1 prime is equal to 1 over A squared times Jx1. Or you can do, similar, well, equivalent formula would be N2 over N1, right? Times R1. The reason why I use this one is because sometimes you get confused and you start then doubting yourself, like, is it N2, N1? So that's why it's better to use the 1 over A squared, at least for me. I'm pretty bad at this kind of stuff, so. All right, but you can do that. So Jx1 prime is equal to 1 over 9.5A again squared times, what was that, J2.0 So Jx1 prime is equal to J 0.022 ohms. Okay, so we got this value and then this value. Then we're gonna build this model. I'm gonna erase this. I'm being lazy now, everybody. Okay, this is R2 JX2 R1 prime JX1 prime. This is going to be V2 plus minus. I'm going to call this for now V1 prime plus minus. This here is 0.005 ohms. J 0.02 ohms. R1 is J 0.0, oops, not J, 0.0054. This J 0.022 ohms. Extend this. Sorry. Plus minus V2. Okay, V1 prime. Okay, so this REQ secondary is equal to R2 plus JX2. R2 plus R1 prime, which is equal to 0.005 plus 0.0054. So our equivalent on the secondary is equal to 0.0104 ohms. And JX equivalent on the secondary is equal to JX2 plus JX1 prime, which is equal to J 0.02 plus J 0.022. So JX equivalent secondary is equal to J 0.042 ohms. Okay. This is what happens when I don't have lunch and I start thinking about dinner. And I'm thinking, okay, I'm gonna stop and get dinner, and then I'm thinking about dinner. My wife gets mad at me because I get dinner late. Makes sense, everybody. Simple, right? All I gotta do now is I can use the same. Can do this. I'm not gonna use this one, but it's the same thing. Again, I've been lazy. Here is primary, here is secondary. In 1 doesn't change, in 2 doesn't change, that's fixed, right? This is REQ secondary, JXEQ secondary. So this is, what did we say it was? J 0.0104 ohms plus J 0.042 ohms. Okay, so that's the answer. You can be this if you want and just have a circuit with here V1 prime. But this is good answer. This is, an acceptable answer. Oh yeah, the other thing that I was gonna say is this. Here's the problem I have sometimes with some books, and I take prompts from books that are realistic, and I take prompts from books that are not realistic, and I make them realistic. Because I see this all the time, like people just put it, and it's like math. The point I'm gonna make on this is, if anybody ever gives you any transformer impedances, okay? Any transformer impedances, whether it's a large, small transformer, and the R value happens to be larger than the X value, that is most likely wrong. And I see it on books. I see books that they just throw numbers, and I go, I get it. You're teaching. I get it. It's math, right? But that's not the case. That is what I call a realistic example. There's no such a thing. The resistance in comparison to the reactance is so much smaller. You'll hear this terminology. They say, oh, the transfer X over R ratio is really high. Yes, because if you divide X divided by R, the number should be high. If you ever get a value, again, when you see the resistance, the impedance of the resistor is larger than the reactor, you got to question that. You got to say, hey, you know what? Maybe you're right. But let me just ask this question. How come the reactance? Because the resistance should be so small that you probably most likely are going to neglect it. Okay? So, you'll see it, right? When you're gonna take other courses and you're gonna have to deal with transformers, so we have work, and you see information like that, I want you to question it, because the losses, the real losses should be very, very, very small, okay? In comparison to the reactive losses. All right, how much time do I have?
10 minutes. Okay, yeah.
10 minutes.
8 minutes.
Are you guys overloaded?
30 seconds.
30 seconds. 30
Okay.
seconds.
All right, I overload you. It's a lot of info. It's not, and it's simple, right? But it's just tedious, right? You just got to remember. But can you do me a favor, for those of you who are here? Can you start writing the formulas? I can see on the midterm, people were not writing formulas, and they probably tried to do that at the very last minute, and they forgot stuff. Start writing them now. These are, and you're gonna use them on the final. I can guarantee it. Okay. We'll continue next week.
Next week is.
The following week.
All right, so I'm gonna upload the midterms so that you guys can check your answers. If I